Electromagnetics lecture series. Today we explore one of the most fundamental theorems in vector calculus, Stokes Theorem, and its significance in electromagnetics. Stokes Theorem is the key to understand how magnetic fields circulate around current carrying conductors and form the basis of Ampère circuital law. By converting line integral into the surface integral, Stokes Theorem allows us to analyze electromagnetic fields more effectively. So in this lecture, we will understand the mathematical foundation of Stokes Theorem, derive the point form of Ampère circuital law, and in the upcoming videos, we will solve the numerical. So let's dive in and uncover power of Stokes Theorem in electromagnetics. So we will have the foundation from the Ampère circuital law, explain the relationship between different magnetic fields and current, simplify the Maxwell's equation, understand the curl in electromagnetics in a better way. So now consider a surface area S as shown in the diagram. Now this particular surface area is broken up into smaller segments whose area is given by delta S, and this delta S areas which we have, we call them as incremental surface areas. Now let us take any one of the area that is shown and let us apply the curl. So by the definition of the curl to any of these incremental surfaces, what are the definition of the curl says? That is the quotient of the closed integral HDL to the area enclosed will be the curl in n axis, where an is this perpendicular vector what we have. So far we have seen in previous cases curl of h in y. I hope this gives a better understanding. Now that we have this, we can also write it RHS. We are very clear now it is going to be a scalar, even though it is a vector. Now if you wanted to write it as a scalar, we can write it as shown here using the an vector. It can be written as a dot product of two vectors so that we can get the scalar, or simply we can take the coefficient of n vector. So both ways we can write it correct. Now let us shift this area to the other side and see what happens. So this delta S, we take it to the other end and we get the equation as curl of H dotted with an dotted with delta S, and this delta S dot an can be taken as delta S vector. Okay, so far whatever we have is by taking only one incremental surface area, it's a line integral HDL suffix delta S, which says that the perimeter of this square, okay, this area, if you do the line integral and dot it with H, it is nothing but dot product of curl of this H here and the incremental surface area delta S. So now what happens to the larger picture, overall surface area, if we want to find out by using the existing equation, how shall we proceed? So let us use the available equation, that is H dot dl delta S is taken like this from the previous slide. Now we want to determine the circulating component for every delta S. One by one we calculate this and integrate. So what happens to the RHS now? That RHS becomes a surface integral. Okay, and we can apply it to the larger area. So this is how our equation will turn up. Now this dl is the perimeter of the larger area. Okay, this dl is the perimeter of the larger area. Line integral h dl will be equal to surface integral curl of h ds. So this is an identity holding any vector field, and this is called as Stokes theorem. So Stokes theorem is a vector identity holding for any vector field, and it states that the line integral of the magnetic field intensity around a perimeter is nothing but the surface integral of the curl of that magnetic field in the given surface area. How to apply this Stokes theorem in the numerical, and how do we evaluate both sides of the Stokes theorem, we shall see it in the upcoming video. Till then, stay subscribed and press the bell icon. Thank you.